Hi guys, Dr. Musk back again. So let's continue our discussion of Chapter 13 in Section 13.6. Now we're going to talk about some reactions of carbon-carbon double bonds, the reactions of the alkene functional group. So in general, reactions of alkenes are addition reactions. So what that means is we are adding two atoms to replace the carbon-carbon double bond. So we break one of those two bonds and replace it with a single bond to two different atoms. All right, you can see here that these are the two atoms of the molecule that we're using to react with the carbon-carbon double bond. In the end, we lose one of the two bonds between the carbons and add a single bond to each one of those individual atoms. So that's what I mean by an addition reaction. We're exchanging the pi bond between those two carbons for two sigma bonds, for two single bonds to those two individual things that we're adding, all right, in the addition reaction. So here is sort of a great study page that shows the different types of addition reactions that a carbon-carbon double bond might undergo. So you can see that we can add H2 across a carbon-carbon double bond. That requires a catalyst, and we'll talk more about that in a minute. We can also add any kind of halogen. So specifically, Cl2 and Br2 work really well with this. F2, it's possible to do it, but most of the time, that's a little too reactive, and you get explosions when you try and add F2 to alkenes. So people, most of the time when they do this, they add Cl2 or Br2. It's easier to control that way. You can also add HCl or HBr across a double bond. And in that case, we call it hydrohalogenation. And in the end, the hydrogen ends up attached to one of the carbons where the carbon-carbon double bonds was, and the halogen ends up attached to the other carbon. So there's some interesting things that we have to look at, especially for these last two reactions, because we have to be careful about where we add the hydrogen and where we add the other things. So in the first case, hydrohalogenation, where does the halogen go and where does the hydrogen go? That's something we have to discuss. And in this last reaction, the hydration reaction, we have to discuss where we add the hydrogen of that water and where we add the OH of the water. So water is the thing that we're using to do our addition reaction. And in that water, H2O, somehow the hydrogen ends up on one of the carbons that the alkene, the carbon-carbon double bond position was. And then on the other one of those carbons, the OH. So we're going to have to talk more about which of the carbons gets which of those groups. So first of all, let's talk about addition of H2 across a double bond. So this PowerPoint is sort of lame in terms of the limited discussion of the catalyst that they give here. So in order for this reaction to happen, in order to add those two hydrogens across the carbon-carbon double bond, we need a catalyst. And the author here is thinking that palladium is normally used. In general, transition metals make really good catalysts for this reaction. So palladium is one that works really well. Platinum is also one that works really well. The commonality between those two is that both of those metals are freaking insanely expensive, all right? So most of the time, nickel also works really well as a transition metal catalyst for these reactions, and nickel's a heck of a lot cheaper. Sometimes, if you're lucky, iron might even work, and that's even cheaper than nickel is, all right? So if you want to use platinum or palladium or nickel when you write down the catalyst that you're talking about here, don't worry about iron because it really depends on which carbon-carbon double bond, whether it's going to work or not. But any of these three transition metals do a really good job as the catalyst for this reaction. And notice that when we add those hydrogens across the carbon-carbon double bond, what we're doing is removing the alkene essentially. We are saturating that carbon-carbon double bond, and now it becomes a carbon-carbon single bond anymore. So the product of that reaction, if there's no other functional group than that carbon-carbon double bond, and we add hydrogens across it, we end up with an alkane. All right, so we have turned our alkene into an alkane by doing this hydrogenation reaction. So here's one example. If we have our basic 2-carbon alkene, ethylene, And we add H2 to it in the presence of palladium as a catalyst. Then in the end, we end up replacing the carbon-carbon double bond with a pair of single bonds to hydrogens. So our second reaction is very much like the hydrogenation, except instead of adding H2 across the double bond, we're adding a halogen, all right? So halogens spend their lives when they're in their elemental forms as diatomics. In other words, they occur in pairs. So if we add Cl2 or Br2 to an alkene, we end up adding a chlorine atom to each one of those carbons, or a bromine atom, depending on which one of the two we add, all right? So this halogenation reaction occurs very easily. We don't need a catalyst like we do for adding H2 across the double bond. And the product, we call it a dihalide because we've added two halogen atoms where the carbon-carbon double bond was. So here are a couple of examples. And these are pretty simple examples, all right? So ethylene or ethene, and we add Cl2 to that, and we replace that carbon-carbon double bond with a pair of carbon-chlorine single bonds. And then cyclohexene, we turn that into 1,2-dibromocyclohexane as the product. So the important thing here is that the alkene functional group functions the same no matter how big or small that molecule is. So what if we had a much, much larger alkene? We could still do any of these reactions of alkenes with it. All right, so let me give you an example. What if we had this big molecule? So notice that right in the middle is a carbon-carbon double bond. What if we added H2 and platinum to that big, big molecule? Notice that those are the conditions that would result in hydrogenation. So even though that's a really big molecule, the same thing is true as if it were a small molecule. We are going to take those two carbons that shared the carbon-carbon double bond and replace one of those bonds with a bond to hydrogen on each one of those carbons. So even in a very large molecule, we can still quickly figure out the product of these reactions by looking for the functional group. The functional group is the part that changes. The rest of the molecule isn't going to change. So let's talk about another reaction of alkenes. So we call this hydrohalogenation, all right? In other words, adding a hydrogen and a halogen in the form of HCl or HBr. And when that happens, just like with the other addition reactions, one of the two atoms is going to get a hydrogen and the other a halogen. So as a result, we are making an alkyl halide as our product of this reaction. So here's the problem, all right? In these two cases, it doesn't really matter which carbon gets the hydrogen and which carbon gets the halogen. But in some cases, it does matter. So let's look at this example, propene. And in propene, we have two different kinds of carbons that share that carbon-carbon double bond. A primary carbon and a secondary carbon. So it turns out that when we have a situation where we have to add the hydrogen and the halogen to two carbons that are different from one another, the hydrogen always ends up on the less substituted carbon in these reactions. So the hydrogen ends up on the primary position, and the chlorine ends up on the secondary position. In other words, this is the correct product out of the two products here. So we don't see very much, if at all, any of that 1-chloropropane. All right? So the hydrogen always ends up adding at the less substituted position and the halogen at the more substituted position. We call that Markovnikov's rule. All right? So the hydrogen will end up at the carbon that is less substituted, and the halogen will end up at the carbon that is more substituted. So let's do another example like that together, all right? What if we had a molecule that looked like this? And to that, I decided to add HBr. So take a second and try and figure out what the correct product of this reaction is. So you can see the carbon-carbon double bond is on the ring, but there's a difference between those two carbons that share the carbon-carbon double bond. That is a tertiary carbon. That is a secondary carbon. And Markovnikov's rule tells us that the hydrogen of that addition reaction is going to go to the less substituted carbon, and the bromine to the more substituted carbon. So the correct product of the reaction will look like this. Notice that in bond line drawing, even though we've added a hydrogen to that carbon on the bottom, we don't show it because we don't show our hydrogens unless they're attached to heteroatoms, all right? But this gives you the correct regioselectivity for this reaction. In other words, we've added the correct atoms to the correct atoms, all right? So very, very similarly, the hydration reaction, where we add water across the carbon-carbon double bond, follows Markovnikov's rule as well. So our hydrogen is always going to go to the less substituted of the two alkene carbons, and the hydroxyl group, the OH, will always go to the more substituted of the two carbons. So this requires a catalyst also. The catalyst in this case is the strong acid H2SO4, sulfuric acid. And let's do a couple of examples where we check Markovnikov's rule. So you can see in 1-propene here, I guess we wouldn't even really need to say 1-propene because there's only really one place where the carbon-carbon double bond could be. But the carbon-carbon double bond is shared from carbon 1 to carbon 2. Carbon 2 is the more substituted of the two carbons, so it's the one that ends up with the OH group added to it, all right? So the hydrogen ends up at the less substituted carbon of the two when we have to pick, all right, in Markovnikov's rule. Let's do a couple of examples where we try and figure out the correct products of a hydration reaction. So we're adding water and H2SO4, which is our catalyst. So in this reaction, and very commonly organic chemists will write one of the reactants on the reaction arrow. If instead you want to just put the catalyst there and then put the water over here, also perfectly acceptable, all right? You might see me write them either way. I'm just trying to give you the heads up. So where are we going to put the hydrogen and where are we going to put the hydroxyl group on that product? The hydrogen is going to end up adding to that carbon, the less substituted of the carbon, a secondary position, and the OH group will add there at the more substituted tertiary position. So hopefully that example has shown you how the selectivity works for this reaction when we do a hydration reaction or when we do a hydrohalogenation reaction. We have to be careful to put the hydrogen on the less substituted of the two alkene carbons, all right?